Okay, so we've got the language down and we know the different types of data. Now let's talk about where data actually comes from. More specifically, how do we design a study that can actually prove something? And before we even get into the details, I want to plant one big idea in your mind. Most studies can only tell us that two things are related. They can show an association, they can show a pattern, but only one special kind of study can actually give us strong evidence that one thing causes another. That difference between relationship and causation is going to be the main theme of this whole section. So keep that idea in the back of your mind as we go. All right, so here's a really fundamental split, and this one matters a lot. There are two major kinds of studies, and the type of study determines what conclusions you're allowed to make. Let's start with the left side. In an observational study, researchers simply observe and measure. They don't assign treatments. They don't deliberately change anything. They just watch what happens naturally. A famous example is the Nurses' Health Study. Researchers followed a very large group of nurses over many years and looked for patterns between their behaviors and their health outcomes. Suppose they noticed that people who drink more coffee tend to have lower rates of diabetes. That sounds interesting. But here's the crucial limitation. An observational study can show an association. It can show that two things are related. But by itself, it cannot establish that one thing caused the other. Why not? Because there may be other explanations. Maybe the coffee drinkers exercise more. Maybe they have different diets. Maybe people with healthier lifestyles are simply more likely to drink coffee. We don't know, because the researchers didn't control those other factors. They only observed what was already happening. Now look at the right side. In an experimental study, researchers deliberately introduce a treatment and then measure what happens. Imagine Amazon wants to know whether a new recommendation system leads to more purchases. One group of shoppers is randomly shown the new AI recommendation system. Another group sees the old system, and as much as possible, everything else is kept the same. Suppose the new system produces 19% more purchases because the researchers randomly assigned the groups and controlled the treatment. They have much stronger evidence that the new system actually caused the increase. And that brings us to one of the most important rules in statistics. I really want you to remember this one. Write it down, underline it, put a star next to it. Correlation does not imply causation. Here's the classic example. Ice cream sales go up during the summer. And drowning deaths also go up during the summer. So the two variables are correlated. Does that mean eating ice cream causes drowning? Obviously not. There's another variable involved. Warm weather. Hot weather makes people buy more ice cream. And hot weather also makes more people go swimming. So ice cream sales and drowning deaths move together, but one does not cause the other. A third factor is influencing both. Because later in this module, we're going to come back to this idea and look much more closely at why relationships in data can sometimes fool us. Okay, so a good experiment needs something to compare against. You can't just try something on one group, see what happens, and call it a day. That's where these two groups come in. First, we have the treatment group. The treatment group is the group that receives whatever you're testing. Maybe it's a new drug. Maybe it's a new feature. Maybe it's some other kind of intervention. That's the treatment group. Then we have the control group. The control group is the comparison group. They do not receive the new treatment. Sometimes they receive a fake treatment called a placebo. Sometimes they receive the standard option that already exists. And sometimes they receive nothing at all. Let me walk you through the example on the slide. In 2021, Instagram wanted to know whether hiding like counts could affect how people felt about using the platform. So, imagine they set it up as an experiment. One group of 50,000 users sees an Instagram feed where the number of likes is hidden. That's the treatment group. Another 50,000 users continue seeing Instagram normally, with the like counts visible. That's the control group. So, what happens? Suppose the users who could not see the like counts reported 18% less anxiety about their own posts. But interestingly, they also posted 12% less overall. Now, here's the question I really want you to think about. Why do we even need the control group? Why not just hide the likes for everybody? Wait a few months and see what happens. Here's why. Without the control group, you would have no way to know whether the change was actually caused by hiding the like counts. Maybe people's behavior changed naturally over those months. Maybe something else happened on the platform. Maybe people's mood changed for a completely unrelated reason. You wouldn't know. The control group gives you a baseline. It shows you what would have happened without the new treatment. And by comparing the treatment group with that baseline, you have a much better chance of isolating the actual effect of the treatment. So whenever you see an experiment, one of the first things you should look for is the control group. If there isn't a meaningful comparison group, be careful about the conclusions the study is making. So, for an experiment to give us strong evidence of cause and effect, there are 3 key principles we need to pay attention to, and these are important. Let's go through all 3. The first principle is randomization. Randomization means assigning people to the treatment group or the control group by chance. You might think of something like flipping a coin, or, more realistically, using a random number generator. Now, why do we bother doing that? Here's the beautiful part. When people are randomly assigned, the 2 groups tend to become similar overall. You get a similar mix of ages, a similar mix of health conditions, a similar mix of backgrounds, and a similar mix of all those other characteristics that could potentially affect the outcome. Ideally, the main systematic difference between the groups is the treatment itself. So if the outcomes end up being different, we have much stronger evidence that the treatment caused that difference, rather than some pre-existing difference between the groups. The second principle is replication. Replication means using enough subjects so that your result is not just a random fluke. Imagine testing a new fertilizer on only 3 plants. Suppose 2 of them grow really well. Does that prove the fertilizer works? Not really. Maybe one plant happened to get more sunlight. Maybe another plant was healthier to begin with. With such a tiny group, random variation can easily fool us. But now, imagine testing the fertilizer on 100 plants in each group. That gives us much more information. Random differences start to balance out, and it becomes easier to separate a real effect from ordinary noise. As a rough classroom guideline, you'll often hear 30 observations used as an important benchmark. But in real research, the number of subjects you need depends on the situation, and very often, more is better. The third principle is control. Control means keeping other important conditions as similar as possible, so that the main thing changing between the groups is the treatment you're testing. Look at the Duolingo example. Suppose researchers want to compare spaced out practice with cramming. They keep the vocabulary words the same. They keep the total study time the same. They keep the app interface the same. The main thing they change is how the practice is spaced over time. Now, suppose the spaced practice group remembers 34% more. Because the researchers controlled the other important conditions, they have much stronger evidence that the spacing itself produced the difference. So remember these three principles: randomization, replication, and control. Together, they help us design an experiment where we can make a much stronger argument about cause and effect. Whenever you look at an experiment, train yourself to ask, were the groups randomized? Was the study large enough? And were the important conditions controlled? Those three questions will tell you a lot about how much you should trust the conclusion. Okay, this next idea is one of the strangest, and honestly, one of the coolest parts of studying human beings. Our expectations can actually change our outcomes. This is called the placebo effect. Sometimes people genuinely feel better simply because they believe they're being treated, even when the treatment they receive is just a sugar pill with no active medication in it. Look at the numbers on the slide. In one Harvard arthritis study, patients who received placebo pills had their pain drop by about 1.4 points, simply from believing they were being treated. That effect was real. The actual medication then reduced pain by about another 1.8 points beyond that. And here's why that matters. If we didn't have the placebo group for comparison, we might look at the total improvement and give all of the credit to the drug. But part of that improvement may have come from the patient's expectations. So we need a way to separate those effects. And that brings us to blinding. Blinding simply means hiding information about who is receiving which treatment, so that expectations are less likely to influence the results. There are two main levels. In a single blind study, the participants don't know which group they're in, but the researchers do. That helps reduce the effect of the participants' own expectations. In a double-blind study, neither the participants nor the researchers interacting with them know who is receiving the real treatment and who is receiving the placebo. And this is often considered the strongest approach. For example, large vaccine trials, including the Moderna COVID vaccine trial, used blinding with tens of thousands of participants. Now, why does the double-blind part matter? Because it's not only the participants who can have expectations. Researchers can have them too. Even without realizing it, a researcher's expectations might affect the way they speak to participants, the way they observe them, or even the way they interpret certain results. Double-blinding helps reduce that source of bias as well. The fewer people who know who received what, the less opportunity there is for expectations to influence the study. So the big idea here is simple. Placebo effects are real. Expectations can matter. And blinding helps us separate the true effect of a treatment from the effects of belief and expectation. All right, so now we've covered the major pieces of designing a strong experiment. The next question is, how do we actually choose the people we're going to study in the first place? And that's where we're heading next.